Great. So welcome to lecture 3. Today is going to be my favorite lecture because we're going to talk about how to train flow and diffusion models. So just as a quick reminder, what did we talk about in the first lecture? We talked about what is a flow and a diffusion model. So we learned that a flow model is randomly initialized with an initial distribution P in it. That's usually a Gaussian. And then you simulate some sort of ODE with a neural network that represents the vector field of that ODE. In a diffusion model, we do the same thing. We initialize with P in it as well. But then we simulate an SDE, which also has an ODE component that's given by the vector field, but we add noise that's scaled by a diffusion coefficient WT at sigma t and a Brownian motion WT. And to get samples, so when we generate objects, what does that mean? We simulate this ODE or SDE from time 0 to time 1. And we're always interested in the final time point. So the object that we want to generate will always be the final time point of that trajectory. Last time, we had 3 objects that we were interested in, and each of these objects had both a conditional and a marginal object. So the first thing was the probability path. The conditional probability path was the one that interpolated between a Gaussian or an initial distribution and a data point set. And the generic example we're interested in is this Gaussian path with a mean scaled by alpha t and a variance scaled by beta t. We have a conditional vector field whose defining property is that its ODEs follows the conditional path. And the example that we had in the case of the Gaussian probability path was this weighted average between z and x of some coefficients that we know. We have the conditional score function, which was the gradient of the log likelihood of the score, which in the Gaussian case just turns out to be the simple average again. So similar to this formula, this is an average between, or weighted average between z and x. Then we transferred all these objects into marginal objects, which means we made the data point set random. So we induced that with our data distribution. Marginal probability path P then interpolates between P init and P data. So something that starts at the initial distribution, ends at the data distribution. It has the formula given by this integral. We have the marginal vector field, whose ODE follows now the marginal path. And we had this formula here where we had the conditional vector field on the left-hand side, and this was this ratio that appears also here, which is always this kind of idea of a Bayesian idea of predicting z given x. We have the marginal score, whose defining property is that we can use it to convert the ODE to an SDE, or at least a training target. And the formula is similar to here, that we have this integral over the conditional score. All right, so that was preparation yesterday. And we will see today that we be translating the marginal vector field and the marginal score function to 2 algorithms that are called flow matching and score matching. And that's going to be the training algorithms that are going to learn these 2 objects. And with that, we're done, and we know how to train a generative model. So we start again with flow models, leading to a method called flow matching. And just as a quick reminder, the conditional vector field is this integral, the marginal vector field is the integral over a conditional vector field multiplied with some ratio. And we had what's called the marginalization trick, where we said that starting off at the initial distribution, we simulate the ODE with this vector field. We follow the probability path. And that's particularly relevant because this path was constructed to end at the data distribution. So the final time point following this ODE will be the data distributions, will be objects that we want to generate. All right. So let's dive in, and let's talk about flow matching. So we have a neural network, UT theta, and theta represent the parameters of that network. And what is our goal? So what I just stated is that the marginal vector field does what we want to achieve. It converts noise into data, and that's what we want to do, right? We want to basically imitate this vector field. So the goal will be of training is that UT theta, our neural network, approximately equals the target, which is the marginal vector field. Okay, so the goal of flow matching training is to learn the marginal vector field. Because we've done that successfully, we will essentially do this when we replace this with the neural network. So, and there's now a natural loss that we can define for this property to hold, and that's what's called the flow matching loss. So how does it look like? Very intuitively, we take a mean square error between these two objects. So we're taking ut theta at a point x, and we're evaluating or regressing it against the target, which is the marginal vector field. And I'm writing here an expected value because during training we need to sample from x and we need to sample some t, right? We cannot do all of them together. We need to choose somehow how to choose the time points t and x where we evaluate this loss. And the first thing we do is we just say we choose t uniformly in the interval between 0 and 1. So we just say every time point accounts in the same amount to our loss. So that's so we're saying we're choosing t just uniformly in the interval between 0 and 1, which is our simulation time, right? The next thing we do is we say we start off with a data point. We sample from the data distribution. What does that practically mean to sample from the data distribution during training? It means we have a data set that's very big. We just randomly draw a point. So in PyTorch, you would have a data loader. You loop over that data loader. That's what I'm writing here formally mathematically as sampling from this distribution. And the next step is how do I choose x? I'm just choosing x according to the distribution that we constructed at time t, which was the conditional probability path. So I wrote here a mean square error between our neural network and what we want to approximate. And now I wrote here how to choose t and x, and as an intermediate step, I'm also drawing a sample instead. Okay? So this is not appearing in this formula, but this is just a way of drawing a point x. Basically says, for some time between 0 and 1, I choose first the data point, and then I'm evaluating it at this intermediate distribution, and then I'm just taking this mean square error. So what's the minimizer of this loss? The minimizer of this loss is this. Like this loss is going to be always, like a mean square error is always non-negative. And it's 0 if and only if this equals this. So the minimizer of this object is what we want. Great. The question is now, is this tractable? The answer is no. And that's a bit sad, but it's actually not a problem, as we'll see in a second. But why is it not tractable? We cannot evaluate this point, not trivially. The problem is this integral here. We have a formula for it, and that's in fact all we need. But the problem is to evaluate this integral. It's a very high-dimensional integral. What we could do, nobody does, but let's just think this as a thought experiment. We could loop over our data set, and for every data point evaluating this ratio, and then take an average over that. But let's say our data set has 30 million images. For every evaluation of the neural network, we would need to do this. It's not a good idea. So basically, this loss is intractable. We cannot compute it. But now we do the same thing as we did in the last lecture. We're taking a conditional loss, and that's going to be the one we actually can compute. So same as before, we have now a conditional flow matching loss. All right, so this. So same as before, we have a loss in theta in the parameters of the neural network, and we have an expected value. And I'm going to now write just t set x, meaning I'm sampling them in the same way as here. Okay, so I'm going to drop some notation. Well, I can also just write it out, but it's going to be a bit small, but it's going to be the same as before. So we're choosing time points and z and x in the same way as before. But now I'm doing something. I'm replacing this object with something I know. What do I know? I know the conditional vector field. The conditional vector field, we had a formula for. It's just this. I just have an analytical formula for this object. I can plug it in. All right, so from this loss to this loss, so from the flow matching loss to the conditional loss, the only difference is I'm plugging in the conditional vector field, okay? So now I made this tractable, so great. But what's the minimizer? Well, it's not, yeah, I would be very surprised if you would see it in a second, because it's not entirely clear. So the question is like, does it even make sense to minimize this object? Because the conditional vector field is not really useful. We don't want to generate single data points. We want to generate a whole distribution of data points, which is what this thing is doing. But now, and that's the main theorem of today, we're going to learn that this thing is all we need to minimize this. That's really at the core of diffusion models with flow matching and the training, is that we can minimize such a loss as a surrogate of that loss. And I want to explain that in a second. The subscript under L here, CFM standing for conditional flow matching. All right. Okay, so theory of today is the flow matching loss equals the conditional flow matching loss plus a value c, but this value c is a constant in, or is independent of theta. All right, so what did I tell you? I told you that they're basically up to some constant the same. Let's try to visualize this. So let's say we only have one parameter. So usually we have a lot of parameters, but let's say we only have one, which is the x-axis. And I told you that the flow matching loss looks something like this. It has some minimum, whose minimizer is the marginal vector field. And then what this theorem says is that there's some constant c, which basically describes the gap to the conditional flow matching loss. And that gap is, though, independent of theta. So it's going to be the same at every point. So that's the flow matching loss. And now I'm adding this gap up. Let me try to do this, make this right. My drawing skills are not the best. All right, so we basically translated this object a bit up to achieve the conditional flow matching loss. So now, if this is the minimizer of this function, I'm going to call this theta star. What's the minimizer of this function? It's the same, right? The value is going to be different. But who cares about the value? Well, some people might, but we don't really care, because what do we care about? We're finding the right parameters. We want to have the right neural network. That's all we care about. The value is meaningless. It's about the minimizer that matters. So basically, we have two core properties that fall out of this. So first of all, what does it mean for the minimizer of the conditional flow matching loss, which is something we can compute? It means that the minimizer is the marginal vector field. What does that imply? So at perfect training, let's say we're training perfectly, right? It's not only approximately, but like we've trained it perfectly. That holds, right? After training, it will achieve its minimum, meaning it's a marginal vector field. What does the marginal vector field do? It converts noise into data. So in particular, if we simulate our flow model, we will have generated data. So we will have converted noise into data, which was our goal. So not only that holds, much more the training algorithm of the neural network. How do we train neural networks? We use stochastic gradient descent. So the gradient of these two objects are the same, because we're taking the gradient derivative with respect to theta, so this constant is going to cancel out. So yes, so the gradients are the same, which means that, so stochastic gradient descent is the same, which I'm now writing as SGD. So your training algorithm will not differ. The training trajectories will not differ if you minimize this or the other loss. Good. All right. So with that, we arrived at the algorithm, and I'm now going to show this to you first in a general setting. Then I'll make this specific with the Gaussian example, and then I'm going to sketch a proof of this statement. That's the plan for now. OK, so let's look. How do we train a flow matching model? We have a data set of samples given. We have a neural network, UT theta, which represents our vector field. Then we loop over our data, which basically means we're at every step sampling a data example set from the data set. So if you were in PyTorch, you would loop over the PyTorch data loader. You sample a random time t from 0 to 1. You sample x from your conditional probability path. So what I'm describing here in the first step is this step. So I'm sampling a random time t. I'm sampling a random data point set, and then an x from my conditional path. Then I evaluate this loss at x against my conditional target, which is the conditional flow matching loss. So I've just replaced this expected value with a sample from these objects, and so it's an estimate. It's a Monte Carlo estimate of that. You have this object, and I'm updating the model parameters of gradient descent. So I'm taking a step optimizer, and there you can choose your favorite optimizer that you usually use in training some sort of deep learning model. That's it. And the power of this is that this is something we know analytically. So at the end of the day, all you do is you're minimizing a mean square error. And that's what really was the power of the flow and diffusion models, is that all you need to do is to minimize a simple mean square error. Like, for example, you've heard of GANs, which stand for generative adversarial networks. There you have a min-max optimization procedure. That's much more complicated than this. This is just, you have a simple mean square error, which you just have to minimize, which is pretty simple. We'll see it in a second, how simple that is. The model UT theta takes as input the time. So the model is a neural network in time and in location x. So it will have two inputs in time and x. We'll see that all in the labs you will code up. You'll see that you have to do two inputs.
I'm just curious, in this procedure where you're sampling T normally at random every time when in this, have people tried like different training strategies where they don't sample T uniformly but kind of build up the path incrementally? Does that work better or worse?
Yes, great question. So just repeating the question real quick. So what about other sampling strategies than uniform? The short answer is yeah, for sure you could do other stuff. It's more an empirical question. A priori, it's not quite clear like what time points do matter more or less, but you could weigh them arbitrarily and sample them arbitrarily often. So you might want to say something like, oh, later time points are more important, so you sample them more often. It happens to be that at least what I see is that most popular is just uniform. Yes. Yes, so we picked this. So if you remember last class, we picked the conditional probability path, and then we picked the conditional vector field that does the job we want. So this is a design choice. We can pick it. We just have to one that fulfills certain requirements. But at the end of the day, there's many other options than this. We will actually see there will be a set of new options, but it happens to be okay if you just choose one, because it does the job that we want. Good, cool. Okay, so I want to make this even more specific now by plugging in the equations that we've seen. And then you'll see that this is actually very simple. So I'm going to derive the conditional floor matching loss for the Gaussian conditional path. Okay, so all right, so how were things looking in this example? We saw that I need to chalk. How are things looking in this example? We had the conditional probability path was just a Gaussian with a specific mean and variance. And if you remember, alpha t and beta t were designed such that alpha t increases from 0 to 1, and beta t decreases from 1 to 0. So what we're doing, we're increasing this mean from 0 to z and decreasing the variance from 1 to 0. So now the formula that we had for this object was a bit clunky, so it's going to take me a bit of time to write this down. Was this? So that's the formula that I had on the second slide, just as a reminder. So I just wrote down this formula for the conditional vector field here again. So keep in mind that we know alpha t and beta t. We just chose them. So this looks more complicated is because we can just plug in equations. And we now use a trick that we can, of course, sample from this conditional Gaussian. But what we can do is we can also sample noise and then add that up. So what we can do is that if the noise is distributed to a uniform Gaussian, so that's now with 0 mean and variance, we can do alpha t times z plus beta t times epsilon, and just call that x. So I'm just defining this to be x. And what's the distribution of this object? It has mean alpha t z, which is this, and it scales the standard deviation, which means the variance scales quadratically, which just means it has variance beta t. So this object is going to be distributed according to our conditional probability path. And all I'm doing now is I'm going to plug in that equation, and I'm going to replace x by this formula. Let's see how this looks like. This is going to be too big. All right, so what I'm doing now, so far it's a conditional formatting loss. I've done nothing here except of plugging in the conditional probability path, which is given by this object. So I'm sampling now from this. I'm sampling from this Gaussian instead. And now I'm plugging in this equation. So what I've done here is I've plugged into this object, or this formula. The microphone still works, right? So I plugged that in. And now what I'm going to do, I'm going to replace x with this formula, okay? So instead of sampling x from this object, I'm sampling just noise and then adding it up. So I'm replacing x by alpha t, beta t plus beta t, goodness, that's not it. Alpha t times z plus beta t times epsilon. Let's plug that in. Right now we just do some algebra. So what I'm going to do now, I'm replacing x by this sum. Okay, let's look at this formula and just appreciate for a second how simple it is. I forgot to say one thing. What's alpha dot? I said it last time, but it might be unusual notation. It's the time derivative of alpha t. And what's beta dot? It's the time derivative of beta t. Just as a reminder of what these things are. So what loss do we have here? What did we end up with? We sample a time uniformly. We sample a data point from the data set. We sample noise, standard noise now, like has nothing to do, like this is going to be the same for all instances. We're plugging in some weighted average of set, data point, and noise into our neural network, and we're predicting the derivative. So we're placing now in this average the time derivative. It's with its time derivative. So alpha t dot, beta t dot, predicting that. So that's pretty simple because we know alpha t and beta t, right? Like we've done, like that we sample the data point, we sample noise, we're plugging in some average into the network and predicting some other average. And to make this even more concrete, let's choose a specific instance of alpha t and beta t. And what's the simplest instance? Alpha t is t, beta t is 1 minus t. Right, I'm saying they only have to go from 0 to 1 and 1 to 0. They fulfill this. So what's alpha dot? What's alpha t dot? 1. What's beta t dot? Minus 1. Okay? So I'm going to plug that in now here. So what's going to be the conditional flow matching loss in this case? So all I'm doing is I'm plugging the choice of alpha t and beta t now in here, which means it's t times z plus 1 minus t times epsilon minus 1 times z minus 1, like plus minus 1 times epsilon, which is just z minus epsilon. All right. This has a specific name, this choice. It's what's called the cond-OT path. Just as an aside, that's related to the idea that conditionally on a specific data point, this is related to the optimal transport path, because this basically corresponds to a straight line between noise and data. So we're just taking a straight line here, which is this object. And what we're predicting is we're predicting a difference. So let's just pause for a second. I feel like this is extremely simple, right? I mean, like this is, I cannot imagine a much more simpler training algorithm than this. We're sampling a uniform time point. We just choose some. We're sampling a data point from our data set. Just draw one. We're sampling some noise. We're taking some point on the line between epsilon and z, between noise and data. And what we're predicting is the difference between those. So let's put this in an algorithm. Well, let's first visualize this. So we have an p init, which we chose to be just noise. We have our data distribution now visualized by these contour lines in 2D. We sample a data point epsilon. We sample a Gaussian noise epsilon. We sample a data point set. We take some point on the straight line between these two, depending on the time, and we're predicting the difference. All right, let's go through this again, because it's really important. Like, I'm not now plugging just equations in, but I feel like it's just good to appreciate how simple it is. So we're looping over the data set. We're sampling a data example set. We sample random time t. We sample noise. We're taking a point in the straight line between z and epsilon, which is we're taking, like, this is the line between z and epsilon, taking some point on this line. We're plugging that into the neural network, and then the neural network has to essentially predict or learn to predict the difference between 2 points, between data and noise. And then we're just updating this as we would do any other machine learning algorithm. I'm just going to pause for a second. Any questions? Like, because you have to implement this, so make sure you understand it. Question? The physical intuition is that yes. Yes, but you have access to more information. At time 0, you have access basically only to the information of noise. At time 1, you have access to the full data point. So over time, you will have, like, you will need to predict the same thing, but the access of information you have is different. That differs across time. But there is a physical intuition, is that this is, like this path here, is a path somehow to go from noise to data. And we took the straight line, but you could have done something different. And if this is your path described by this function, that's the velocity of that point. So what you're essentially doing is you're predicting velocities. Given noise and a data point and a path, somewhere on this path, you need to predict the velocity that you are currently at. But in the case of a straight line, the velocity is just a difference. It's just this vector. So it's going to be even simpler. Cool. Okay. So, no questions? Question? Yeah. There are initial diffusion models were doing non-straight lines. So it's what's something called a variance preserving path or variance exploding path. And in some sense, so there's an intuitive answer that straight lines might be better because that induces less error when you simulate an ODE. But really, it's a more empirical question of like you choose different things and then select the best one.
In the lab, you will not be using a path.
Thank you. Cool. Okay, great. So just to recap, we had a flow matching loss. Our goal was to train the marginal vector field. Can't do that. Don't know what the value is. We found a tractable alternative, and for now I just claim to you that they are the same up to a constant, which means that minimizing the conditional flow matching loss will also minimize the flow matching loss. We then instantiated that for a specific case of a probability path, which was the Gaussian probability path, which in this case led to the simple formula of some average and predicting the velocity that I just mentioned. And in the specific case of this linear interpolation, leads to this thing, which is commonly called the Kondo T path. And just to give you an example that this is not some exotic algorithm or too simple, I didn't break anything down here to make it simpler. This is the algorithm that Meta's Movie Gen, for example, is using. Like these videos were generated with a neural network that was trained in the algorithm that I showed in the previous slide. And in the same way, Stable Diffusion 3 uses the same algorithm. So like it's, how to say, there's a lot of complexity behind it. We've seen this yesterday, but it's somehow hidden in a rather simple algorithm. I think that's really the beauty of this. All right, question? Oh, I see. So you first make the choice of a set, of the data point set that you sample randomly. And then once you sampled it, then you make everything conditional. So the whole name of the game is like, we just always sample a data point and then act as if this would be our distribution. just regress only against this data point, only against the conditional vector field for this data point. But by looping over many different data points, on average, we're going to get a whole distribution. Oh, so noise came from the fact that we have a Gaussian distribution. So if we want to sample from a Gaussian distribution, it also, you can rephrase it as scaling this value set with alpha t, which is its mean, and scaling it with the standard deviation. So that's just a fact about Gaussian variables. Implicitly, we've chosen the p init to be a Gaussian here. So in this example, it's always going to be a Gaussian. Okay, good. I wanted to quickly sketch the proof of theorem 4.1, just because it's important. But it's not going to be relevant. Like, you don't have to know this. Essentially, what we're doing here, we're using this formula twice. So if you have two vectors a and b, and they lie in Rd, and you take the square, the mean square error, sorry, just squared error, you get this formula, right? That's basically the quadratic formula, but for dot products. And what do we do now? And I'm going to give you an abbreviated notation here, just because we don't have tons of time. So this, we apply this statement here to this. All right, so I've applied this general formula onto this expected value. I'm now doing the same thing for the conditional floor matching loss. Sorry, it takes a bit of time to write this down. Okay, so I applied the same formula twice. So these two objects are basically the same right up to this conditional vector field. So I've applied this twice, this top formula here and here. Okay, so the only difference you see here is that here we have the conditional vector field, and here we have the marginal vector field. And now what I'm going to do is I'm going to cut out constants in theta, because I want to show an equality up to constants, right? So The first thing, the observation is that's a constant in theta, that's a constant in theta. So let's get rid of that. Next thing, this and this is equal, right? Because that just depends on the neural network. That appears in both losses, all good. So we can cut that out because they're going to be equal. So now the name of the game is just going to show that this term and this term are going to be equal in expectation. So the proof proceeds, you have it in detail in the lecture notes, by showing that this middle term here is the same. And why does that hold? It holds because this object, this dot product, is linear in set. Then you can swap out expectation values. I can, after class, if you want, I can show it in more detail. I just don't have time here. But in the lecture notes, this is described in detail. But basically, you have to show that this middle term on this blackboard is the same, which is the fact which holds because dot products are linear. Good, cool. All right, let's proceed to okay, I made the statement here. You use Jensen's inequality. It's less important that this is bigger than 0. It's just important that it's a constant. It's important in the sense that if you train a model like this, the loss you're minimizing will have a constant that is bigger than 0, so the loss will never reach 0. So this loss can be 0. This loss cannot be 0 because this is bigger than 0. Wait. Sorry, I swapped the constant on each one side. It's the other way around. So it's negative, but it does, like, for our purpose, it doesn't really matter. Like, it matters that it's a constant. But basically, because this is negative, this is going to be always positive because this is 0 at the minimizer. So you show that there's always a positive gap between the two. What are you saying? There might be cases when this happens. This is, could be interesting. But on average, on general, no. Like on general, we just do what we just discussed. No. All right, maybe one last thing. How do we sample from a flow model? Like we've just trained it, how do we do it? Like what do we do to generate objects? Exactly, yeah. We already discussed that. We're done. Like, remember lecture 1, how do we sample from a flow model? As you said, we simulate the ODE. We've already have an algorithm for that. So, great. We can move on. So, just to pause a second, we now have the full pipeline of this generative modeling for flow models. And now we're going to try to do it for stochastic differential equations, so with diffusion models, and extend it a bit. And I'm going to make that a bit quicker because the principles are essentially the same. All right.
Does anyone use that sampling algorithm in practice?
The Euler method?
Euler.
So the question is whether people use Euler method. Yeah. Initially they were, but nowadays you want to, so what you want to minimize the number of evaluations of your neural network, and that means as many steps you have in the simulation, and you want to minimize that. And what people usually use is like higher order ODE solvers. So like instead of using the Euler method, at least when you care about efficiency, you would use something like Ewan's method. It's in the lecture notes as an example. Or you even like distill the model more. But yeah, you would usually use some sort of higher order solver, but it's usually not very different. There's different ways. There's adaptive solvers and non-adaptive solvers.
Like these Fibonacci models are deterministic in a sense. Like once they're trained, if you sample a point and then generate a sample for it, it'll always be the same sample.
Yes. So the question is, to what extent are flow models deterministic? And they are deterministic once you sample the initial point. So once you sample the initial point, you always get the same point. So there's a one-to-one mapping between the input or start point and the output, which is given by the flow. Like it's this flow map that we discussed. All right, cool. So Right, let's recap what we had for diffusion models. We had a marginal score that we needed to learn, and it was basically had the same formula than the marginal vector field, just replaced with the conditional score function. So this formula looks exactly the same. And we had this STE extension trick with this monstrous formula here, which basically said, I'm starting with an initial condition in the same way. I'm following an STE, but now I'm injecting some noise, and I need to add some correction term to account for the fact that I'm adding noise. And I'm following the same probability path. So I do the same thing. And in particular, my endpoint will have the data distribution. So what do we do? If we want to simulate an STE like this, I've just showed you an algorithm to train this object. Let's learn this object. So what do? We have a score network, ST theta, where theta are the parameters again. And as before, our goal is that ST theta approximates the marginal score. And how would you do this now? Given what you just saw, let's think for a second. Like the marginal score has the exact same formula for the marginal vector field. The same trade-offs hold. We have a marginal loss and a conditional loss. Now I'm going to do the same exercise again. I'm going to define a marginal loss, conditional loss. I'm going to show you that they are the same up to a constant. Let's make this specific. So score matching loss. We sample t, set x in the same way as before, so I'm not going to write this down because it's a bit long to write down. We evaluate the neural network. We regress against the marginal score. So same way, we have a mean square error. And then now I'd like to call this conditional score matching loss. But unfortunately, people don't call it that way. They call it denoising score matching loss. So just keep in mind that it's an equivalent thing, but with a slightly different name. And I'm going to write down now the exact same thing. But replacing, what do I replace this with? Replacing it with the corresponding conditional object, which is the conditional score. Why is that tractable? Because we know the conditional score analytically. So a priori, the minimizer of this object is good. It's the marginal score. Is it tractable? No, it's not, because computing this integral is very hard. What's the minimizer of this object? In the same way as before, at least a priori, we wouldn't know. But it's tractable. And now, same exercise. Which is the next theorem for 2. Score matching loss equals denoising score matching loss up to a constant. And now, this constant is truly negative. So same thing as before. now the same exercise holds. So like, just to reiterate, first property, the minimizer of the denoising score matching loss fulfills that the corresponding score network is equal to the marginal score. And the same thing holds again, that the gradients are the same. But this is the core thing. Like once we've trained into perfection, we've learned the marginal score. How do I prove this? It's a trick question. I'm not going to give you the proof, but how would you do it?
It's exactly the same as 4.1, and you just change.
Exactly. Like, it's exactly the same thing. Like this function, this formula is the same as before. We've defined everything the same, just replace the marginal and conditional vector field with the marginal and conditional score. So you only have to read one of the two proofs, and then we're done. Of course, it's good to do it, but there's no real need because we've just replaced same objects into one another. Good. All right, so let's take a look on how that looks like. How do you learn scores? So we do score matching. We have a score network, ST theta, same exercise as before. We loop over a mini batch of data, sample a data point, sample a random time t, sample from the conditional probability path, computing this loss, which is just the mean square, the square error between ST theta and the conditional score. Then we update the model parameters. And then we loop over this on and on again. And the same principle holds again. We don't score only conditionally per data point, and we only ever regress this object against this conditional score. But the effect of training iteratively over many, many data points is going to be, you're going to learn the corresponding marginal object. When I first saw that, I found that a bit magical, actually, the same way as for the flow matching loss. Like, this object never appears anywhere. Like, this is a formula. We never have access to it. But implicitly regressing against this object, we learn this marginal object. I think it's very magical that you learn something you've never seen. But over the course of training for a long time, you will have approximated it. Good. Somehow I always feel that the microphone is off, but it's on, right? Yeah, it's on. All right, same exercise as before. Let's make it specific for Gaussian probability paths. So let's take the conditional score, which is given by this formula. Shown this last time. This was in the first two slides. And now I do the same trick as before. Gaussian noise, this sum is going to have this distribution. It means if I have a Gaussian noise variable, I'm scaling it by some beta t parameter. Its variance is going to be beta t squared. Its mean is going to be whatever I add up. Now I'm going to plug this again into the denoising score matching loss. So I'm going to regress this against the conditional object, which is on the top here. And then I'm doing the same trick that I've done here. And I replace x with the corresponding object here. So x becomes this sum. X plugged into this equation is going to be the noise divided by beat beta t. So what I'm doing is I'm taking some average between the data point and noise, putting that into the network, and learn to predict noise divided by some constant. Pretty simple, right? And the cool thing is, well, maybe just as an aside, I told you that it's called denoising score matching. Maybe you now understand why it's called denoising score matching, because the method initially was actually found only for Gaussian probability paths, And in this case, you just learn to predict the noise that was used to corrupt the data point. That's why it's called denoising score matching. And it's like this terminology is just as stuck, but in this case, you really see why it's called that way. Let's see. Okay, training algorithm, in this case, same way as before, just that we now here predicting noise divided by beta t. That's what we're doing. It might be worth like mentioning that this is numerically unstable for beta t small, like for small beta t, and beta t is small for times close to 1. If you look at this graph, so for times close to 1, it was early on realized when diffusion models were developed that this is numerically unstable, and there's some tricks to do it, which is there's details in the lecture notes, but essentially you're scaling this by beta and then dropping a constant. Like, I just want to make you aware of the fact that this loss can be numerically unstable for times close to 1. But it's not something you have to worry about, but you will see it in papers. They refactor the score network into something what's called a noise predictor, so you basically drop that constant. Good.
Beta goes from 1 to 0.
Yes.
So as you go forward in time, that beta term is getting smaller.
Yes.
So the amount of noise from the epsilon is having a bigger effect over time.
Yes, great point. Yes. So this is gonna blow up, right? This is gonna go bigger and bigger, and that's why denoising score matching initially was thought, or is still the case, if you just want to learn the actual score, is going to have extreme high variance for beta t, like for no noise levels. So the amount of noise that we add is determined by beta t. If we add very low amount of noise, then it's going to blow up. It's going to have very high variance, and it's going to be tricky to be learned. There's tricks around that, but that's why initially denoising score matching was not thought to be, like historically, not once diffusion models developed, was not the case, but that was, like the score matching was developed before diffusion models, and there this was thought to have high variance.
Can we avoid having to train both the score function and our
Yes, I'll get to that. I'll get to that in a second. So the question is, can we avoid learning both of them? And the answer is yes, for the specific case of Gaussian paths. There is a specific case where you don't have to do this, and I'll discuss. Yes. So there's very many different frameworks to look at the fusion model. I'll discuss that actually in a second. I'll get back to it. Yes, so in principle, for the general case, I'm going to talk about this next. You will have to learn both of them, but in the case of, the most important case of the Gaussian paths, we can convert them into one another. I'll talk about this in a second. But even if you have to learn both, keep in mind that we can just put them in the same network and then just make the output. Let's say we have one output per pixel, which is make 2 output per pixel for an image. So it's not going to be that much more computationally expensive. Okay, so what are we going to do now? We're going to plug in our neural networks into the SDE that we had before shown to follow the probability path. We're plugging that in. So we're plugging in the neural network that represents the vector field and the score network. And after training, at least training perfectly, we know that XD follows the probability path. So we'll end up with data at the end. Cool, let's see an example of that. I showed you this visualization already, but how was this model trained? Like how do you train models like that? You do score matching and get stuff out like this. Cool. All right. So now I want to. So this is it in terms of theory. I just want to give you. No, there's one small thing that we still have to discuss, but I want to give you a bit talk about a specific case of denoising diffusion models, and then talk a bit about how this all places itself in the literature out there. You might go out and read other papers, and we want you to not be confused. So First of all, denoising diffusion models. In our terminology, or in this general terminology, is a diffusion model with a Gaussian probability path. So it's this standard example we had. So the standard example we had was the case of denoising diffusion models. And for many people, a denoising diffusion model is just diffusion model. So if you go out there to some machine learning conference, for many people, if they say diffusion model, they mean actually this thing. So they mean have a specific instance in mind, and you should keep that in mind that there's many, many different terminologies, there's many, many different approaches, and people will talk about the same thing in a different way. It's just important to keep in mind. All right, so what's a special property about these denoising diffusion models? And that's the last theoretical thing for today that we need to realize. And thank you, Cole, for bringing this up. So let's look at the conditional vector field and the conditional score again. And let's make a very simple observation. They're both averages of Z and X with somehow weighted, right? This is basically, both of them have a formula of the form lambda 1 times Z plus lambda 2 times X, and the other one has lambda 2 times Z plus lambda 2 times X. Right, there are specific coefficients there, but let's ignore them for now, right? And this has an implication, is that we can convert them into one another. So you can express, in this case, the conditional vector field in this format, in form of the conditional score. This is algebra. This is not obvious, but like you just have to plug in the equation to see that this will fall out. The same way holds if we integrate over Z with our formulas for this object and this object. Same holds marginally. Same holds for the marginal vector fields. What does this imply? Implies that we can convert post-training the marginal vector field into the score network and the other way around. And you're going to do this in lab. So we're going to do both flow matching and score matching, but you'll later realize they're actually the same for this specific case. Not in general, but for the specific simple case, they're the same. So in denoising diffusion models, which is this example, we don't have to train the vector field and the score network separately. They can be converted into another one post-training. And Cole's question regarding score matching and flow matching, whether they have to be the same, was related to the fact that the first generation of diffusion models did only score matching, because they were relying on this, implicitly relying on this Gaussian probability path, and then could convert stuff into one another. So they only did score matching. So if you read early diffusion papers, they just talk about score matching, nothing else. All right, so just to reiterate, we arrived here at a full end-to-end training and sampling algorithm. So we have a generative model now. What you can do is you can generate samples from the data distribution. The question is now, what are next steps? So next week is going to be more applied. We're going to talk about specific choices that you can make for specific applications. So first of all, neural network architectures. So far, the neural network was always just some function, ST feeder, UT feeder. I didn't really specify what this function is. We need to make choices, and there's different considerations to make. We're going to talk about them. Then we're going to talk about how to condition on a prompt. I told you that this was generated with a flow matching algorithm, but there was a specific prompt, something like a monkey swimming in a pond, having some boat, small sailing boat, or something like this, right? So you want to have a prompt like this and have something that fits to that. It's actually relatively simple to do that, but this is an important thing to understand. So this is one we're going to discuss on Monday. And we're going to also discuss on Monday how to build an image generator or a video generator like this. These are the two ingredients. And then we're going to talk briefly about like how this works. Also, I wrote an email. I sent an email this morning. We have now a guest speaker on Monday as well, who's going to talk about reinforcement learning with human feedback or reward fine-tuning for diffusion models. So you know, for example, that JetGPT was fine-tuned with reinforcement learning from human feedback. And the same way you can do something with flow and diffusion models. That's not going to be relevant to pass anything in this course. It's just going to give you a taste of what else can be done. So it's going to be at the end of the last 30 minutes of Monday's lecture. And then we're going to talk about specific applications. We have guest lectures, so for robotics and protein design. And these are really, really cool people. I would strongly recommend you to come because they have really shown what's possible with these models that go beyond just image generators in other areas. Good, cool. So we have a few minutes left, and now I wanted to quickly talk about other approaches or literature overview. So first I want to say we've put stuff in the lecture notes in detail. So if you want to see how what we learned in this class relates to other stuff, there's like several pages of text about how what you've learned in this class relates to other models. So just to reiterate, there's a whole slew of different flow and diffusion models. Like, don't be confused to go out there and talk to your colleague, and you have a completely different language. That's unsurprising because unfortunately this has been discovered in many, many different ways. But that's just important to keep in mind. I just want to make a few points. So the first diffusion models only use discrete time. So there was not even an ODE or SDE. They were discovered in a slightly different way. There was a physics approach. There was an approach that used what's called Langevin dynamics. It's just important to note that they use discrete time steps. So essentially what this corresponds to is a discretization of an ODE or an SDE. And you arrive there at an approximate loss, which is what's called an elbow. It's described in the lecture notes in detail. But it's just to keep in mind that like they had a slightly different approach, but their loss function was then approximate only. But it was later shown by the first SDE-based model that in the limit, you recover a stochastic differential equation, and then the training becomes exact. Cole's question was related to what's called the forward and the backward process. So the first SDE-based models used time reversals. They didn't use this construction of probability paths. They used construction by time reversing SDEs. It's a bit more complex what it means to time reverse something. But it's important to note that their construction was slightly different. But essentially, they constructed probability paths in a slightly different way. You couldn't just sample from it, but you had to like think about it as a simulation of a Markov process or stochastic differential equation. And the final, and I personally find that the most annoying bit, is that they use often an inverted time convention. So they start with time 0, which is where the data is, and then they flip stuff. So that's often, when I read papers across these different interpretations, that's the most time I spent, because I first have to think about, oh God, okay, now what time convention is used? So keep that in mind. There's a lot of different ways of doing this, explained in lecture notes in more detail. What we're presented you here was related to what's called flow matching. Well, we talked about flow matching, so unsurprising. And also a framework that's related to it is called stochastic interpolance. And these are basically constructions that are similar to here, where we can really convert arbitrary distributions into others. So P init can be anything. P data can be anything. We can only work with flows from the get-go. We never have to think about what a stochastic differential equation is. That's why also we made this choice, because stochastic differential equations are a bit hard. Ordinary differential equations are easy. And flow matching allows you to never even think about stochastic differential equation. And I would make the claim that they're arguably most simple. They're most closest to what's actually happening. Although that's my subjective statement. That's not something that's objectively true. But what's definitely true is they're the most general ones. Good. So as we said, we can convert arbitrary distributions into one another. And I just want to give you an example, like, why would we care about something that's not only a denoising diffusion model? Like, a denoising diffusion model always starts with P init. What's P init for a denoising diffusion model? It always starts with some sort of Gaussian. Like, the only thing we can start off with is noise. That's for what we write as DMMs, denoising diffusion. Wait, DDMs, denoising diffusion models. But there might be other cases where your initial distribution is much, much, much more interesting. And there's a lot of people exploring that in the image space, in the audio space, in the sciences a lot, is where your initial distribution is something meaningful in itself. So for example, you can think about a video without audio being converted to a video with audio, a low resolution image to a high resolution image, an unperturbed cell, if you have like biological data, to a perturbed cell. And here's, for example, an example from the works from Michael Albergo from stochastic interpolance, where you convert only partial noise in an image to a full image. So you basically convert that. You see it's step by step being recovered to its full high resolution image. So you basically unmask certain parts of it. Good. I think at that point I would say we can have a few questions. And with that, we would see each other on Monday again. But keep in mind, this basically ends the more theoretical part. And next Monday, we're going to talk about specific instances and applications. As a reminder, there's no lecture on Tuesday. We want to reduce the amount of additional methods. We're going to make an office hour in this room to allow you to code up the labs. Because really, like, implementing this is really the most fun and core thing. Good. Cool. All right. If you have questions, just come to the front after class. Thank you.